Generative AI has evolved from single-model text chatbots to complex, multi-agent workflows executing across thousands of synchronized accelerators. In these highly distributed environments, raw GPU calculation speed no longer dictates when a task is completed. As the workload progresses, the critical path to execution constantly moves. This chart maps the moving critical path. During prefill, the workload is intensely compute-bound, but generating answers requires moving caches and decoding tokens, shifting strain to network bandwidth and memory. Finally, complex tasks rely on external tool calls and security verifications, introducing new latencies. Optimizing only one piece of hardware, like increasing raw GPU flops, merely moves the bottleneck to the network or storage layer. This causes deadline misses and failed outputs despite high raw throughput. A foundation model operates in a purely semantic space. It relies entirely on physical infrastructure to translate its probabilities into executed work. This diagram splits the system into two distinct planes. On the left, the generative AI model predicts tokens or code. In the center, the Predictive Tensor Control Plane forecasts whether underlying physical systems can deliver that artifact on time, within budget, and under established policies. Next-generation systems now require a dedicated operational assurance layer to convert semantic intelligence into a guaranteed generative yield. Orchestrating compute, network, storage, and security domains simultaneously introduces a severe data problem. Every vendor platform emits heterogeneous telemetry at different frequencies. This visual illustrates the challenge: a continuous, high-dimensional stream of incompatible state variables pouring in from workloads, hardware nodes, network switches, and identity systems. To process this volume, the architecture applies classical engineering analytics derived from tensor networks. It does not use quantum computing. It uses classical tensor mathematics to manage state compression. Incoming state data is contracted into a pattern-of-life tensor train. This approximates massive arrays into low-rank memory cores, reducing storage. The tensor state then translates into a typed dependency graph, mapping how hardware and identities interact. By converting raw telemetry into graph geometry, the system can calculate operational distance, explicitly measure network reachability limits, and define physical capacity boundaries across the cluster. Without this compact tensor mathematical representation, predicting a system failure or mapping a security risk across a massive multi-vendor environment remains computationally impossible. If a central intelligence tries to directly manage every hardware component, it will inevitably race against the native schedulers and congestion controls already built into the silicon, causing system instability. This diagram maps the authority partition, a strict hierarchy preventing the predictive plane from fighting native hardware loops. The PTCP slow path sits near the top, ingesting tensor state, forecasting bottlenecks, and compiling policies. Beneath the domain adapters is the fast path. This layer sits directly on host nodes and network gateways, executing those pre-authorized rules instantly, without ever waiting for a remote cloud forecast. This fast path relies on verified native operating system mechanisms, such as eBPF on Linux hosts, to rapidly drop unauthorized packets, meter traffic, or redirect data flows at the local level. At the base, the native infrastructure, the switches, optics, and GPU silicon, retains ultimate physical authority. Microsecond-level safety and routing decisions belong here. Strict timescale separation ensures that slow, complex intelligence provides the forecast, while fast, localized enforcement acts on it, avoiding latency spikes and system collisions. This predictive framework maps directly into real-world infrastructure products across 4 specific applications. While it optimizes token economics in data centers and manages autonomy at the physical edge, its most critical application addresses infrastructure defense. Modern generative systems deploy autonomous agents that persist over time, hold identity credentials, and interact with external APIs. A compromised or hallucinating agent uses those legitimate permissions to execute unauthorized actions directly against the core infrastructure. The zero-day application suite mitigates this through a mechanism called topological caging. Using the previously established dependency graph, the system calculates a hard mathematical boundary around the exact tools, network segments, and data stores an agent is authorized to reach. If an agent attempts to establish a connection outside this approved dependency graph, the fast path instantly revokes its network reachability. It evaluates the structural geometry of the request, entirely ignoring the semantic content of the agent's prompts. By treating agentic security as an infrastructure geometry problem, Compromised multi-agent workflows are physically contained, even when semantic model alignment completely fails. Granting an automated predictive system enforcement authority over a production enterprise network carries immense operational risk. The architecture dictates that the predictive model must be entirely falsifiable. It must continuously calculate its own error rates, declare its uncertainty, and abstain from action when its confidence drops below defined thresholds. This evidence ladder details the proofs required before earning network control. Deployment starts passively, observing telemetry, replaying faults, and testing counterfactuals as a shadow twin without altering traffic. Once proven, it advances to tightly scoped canary deployments with instant rollback. To reach full closed-loop integration, the predictive plane must demonstrably outperform the strongest native hardware baselines in rigorous, real-world benchmarks. Dominance in the next generation of AI depends on a dedicated, mathematically falsifiable infrastructure layer that guarantees the secure and reliable delivery of model outputs into the physical world.